Okay, good morning everybody. We are going to be getting into bonding today. We're starting into our new unit. I apologize for my voice this morning. It's a little rough. I'm not sure how it's going to hold up, but I'm going to try and go ahead and get through this. We are going to be talking about bonding in this unit. This is where we start talking about ionic bonds, covalent bonds, metallic bonds, and all of the different Lewis dot structures that go along with them. So this is going to be kind of like an overview into these things and some of their characteristics today. So with bonding, the reason that things are going to go through bonding is because what they're trying to do is they're trying to achieve the lowest possible energy state that they could get into. So if we think back to thermodynamics, we know that we have this idea of the hill. We have chemical reactants at the top of the hill. They are unstable. And when things are unstable, they can naturally go down the hill to a more stable state. That is the whole reason that things bond. Right, we saw that exothermic reactions were favorable. Things that had a negative delta G for Gibbs were favorable. We want to lose that energy and go to a more stable state. So we'll find that most of the time when bonds are forming, they're exothermic. There are some endothermic reactions out there, but most of them are exothermic. We're also going to see that when they are going through these bonding events, what we find is that most of the time the elements are trying to achieve their octet. This seems to be the most stable state. The octet is when the s and the p orbitals are completely full. And so we know that some good examples of this are our noble gases like neon and helium and argon. These gases, they don't ever react with anything else because they already have this octet. They are already at the lowest possible energy state, and so they don't need to do anything. Now, Coulomb's law is going to be used quite a bit again in this unit. We saw Coulomb's law before a little bit differently. We were using radius instead of diameter, but Coulomb's law is going to be used to describe bonding and bond distances and things like that. So I went ahead and I threw it back in here again. We're not going to focus as much on Coulomb's law right now as we will in some later dates. So first off, let's go ahead and talk about their electrons and how they might go about achieving this octet and the lowest possible energy state. So with Lewis dot structures, remember that Lewis dot structures are showing our valence electrons. So what the heck was a valence electron? Well, a valence electron is the electrons that are found in the outermost energy levels. So if we're talking about electron configurations, let's say, for example, that we're looking at the electron configuration for magnesium. Remember that we liked to abbreviate that. So if I was going to abbreviate magnesium's electron configuration, I would say that it starts with neon, and then it goes to a 3s2. What I'm showing here are the valence electrons. If we were doing this for something like chlorine, chlorine would once again start at neon, and it's going to go to 3s2, 3p, and it should be 5. 1, 2, 3, 4, 5, yeah. And so once again, these things are my valence electrons. And so what we do when we draw Lewis dot structures is we simply take our element and we put those valence electrons around the atom. Now, when we put the electrons around the atom, we're going to use the same type of things we did when we were adding arrows. We're going to sort of picture 4 places around the atom. So each of these 4 places is representing the s, and then remember that there are 3p orbitals. So those are 1, 2, 3, and 4 locations that are around. Now, the order that we fill them is going to be a little bit different because a concept known as hybridization. We're not going to jump right into hybridization right now. That's a whole nother day. We're going to keep it real simple, and hopefully you'll remember this from honors chemistry or first year chem. But when we go to put these things in, since I have 2 valence electrons, I just need 2 dots. The dots can go anywhere around the magnesium as long as I'm filling up one side and then the other, right? So you could have something like this. You can have something like this. It's all the same. We just don't want to see something like this. Now, technically, this isn't really wrong because there are just 2 electrons in the s orbital, but the s orbital ceases to exist when this thing actually goes to bond, which is why we're drawing Lewis dot structures, is because our atoms are going to be bonding, and it hybridizes. Basically, the s's and the p's start blending together. But like I said, that's a different day, so don't worry about it too much. So right now, we're just not going to do this, right? We're going to put a dot in each location. So we're not going to do this. So if I'm looking at this one, we've got 2 valence here, 5 here. So we have 7 valence electrons. So I'm going to go 1, 2, 3, 4, 5, 6, and 7. So we're just putting 1 on each side, and then once all 4 sides are full, we'll start pairing them up. So that's how we're going to go about it. Now, when we're looking at these dots, we will have a couple of vocab words for us. We have a lone pair. Okay, so a lone pair is defined as this pair of electrons, and normally it doesn't do much in the way of bonding. And then we have a bonding pair. So right now, this right here is just a lone electron. It's not a lone pair, but it will turn into a bonding pair. So things are going to happen at this location. So we only see bonds forming most of the time around single electrons. That's going to turn into a bonding pair, and that's where all of our action is going to be taking place. So once I get something like this, once I have these Lewis dot structures, we know that they're going to be trying to achieve their octet. And so for those of you who don't remember that the octet, oct is 8. 8 seems to be the magic number. So they're going to be gaining electrons, losing electrons, sharing electrons, doing whatever they can to reach that most stable state, which for the majority of elements is going to be 8. So if they are exchanging electrons, so for something like magnesium, we can see that it's got 2 electrons. That means it has to gain 6 to get to 8. That's not going to be the easiest thing. Versus, if you think about magnesium, it's got a bunch of rings here. So we're in the 3rd ring with an electron and an electron. But underneath, this one is full. This one already has 8. So what magnesium's going to do is it's going to lose those 2 to expose the full shell underneath. Versus chlorine only needs to gain 1. So like these 2, this is a perfect example of an ionic bond. This guy wants to lose, this guy wants to gain, the electron's just going to come over here, right? We're going to pass the electron over, and this is going to form positive charges, and this is going to form negative charges. This is what we see in an ionic bond. So in an ionic bond, we get what's known as a lattice. And in this lattice, we have this alternating cation, anion. It's a very ordered structure, and it gives us very significant and unique properties to ionic bonds. So the first property should be really obvious. This real, uniform alternating charge is extremely organized, and it's going to give us these crystalline structures. So when we're talking about ionic bonding, we're normally going to have a metal and a nonmetal because one's going to want to give away to the other. And once we give that electron away, it's all about this electrostatic attraction, and we've got a positive attracted to a negative. There's no physical connection here. We don't really know which one is attached to which. It's just this alternating charge. And so because there's no physical bond between the two, they have extremely high melting points. These things turn into one giant structure. It's not a lot of little individual things. So if I want to melt something, I literally have to break an ionic bond in order for this to melt because it's one big giant structure. So it takes a ton of heat to melt these things. We also are going to see that they're these crystals, and because they're these crystals, they're going to be really, really hard because these charges don't want to move around. You don't want to put a positive next to a positive, but they're also going to be extremely brittle because if you do hit this with a hammer, and this thing moves over one place, and this thing moves over one place, and this thing moves over one place. What you just did is you put a positive next to a positive, negative next to negative, positive next to positive, and they repel, and the whole thing shatters. And finally, we get conductivity. Conductivity means that electricity can go through your substance. Now, in order for electricity to go through a substance, we have to have moving charge. And so for moving charge, we need to dissolve this thing in water. You have to be able to split these things up so that the positives and the negatives are flowing and moving and allowing those electrons through. Now, what if we have two things like chlorine? What if we wanted to do Cl2? Both chlorines want to gain. Nothing wants to give up. So in this situation, since they both want to gain, we're going to go into sharing. So when we share, our electron clouds are going to overlap, and you'll see that we get a physical connection between the two atoms. Now, this gives us very different properties, this physical connection. So we're not necessarily going to have these high melting points or these crystals that we saw in ionic bonds. Now, if we're looking at something like water, you can see that there's one distinct unit here and there's one distinct unit here. What's holding these things together? Well, a small, weak hydrogen bond is holding these things together. So if I add a little bit of heat in order to get this solid to turn into this liquid, all I need to do is break that simple little hydrogen bond between molecules. A hydrogen bond is nowhere near the strength of an ionic bond. So these things melt very easily. They're also not going to be crystals, right? So, and because they don't have any charge, they're never going to conduct. Now, we also have another type of covalent bond, though. It's a lot more rare, but it is worth noting. It's a network covalent bond. A network covalent bond actually takes on more characteristics of an ionic bond because instead of lots of little individual molecules, it links together like we saw here into one giant molecule. I can't say that this is an NaCl or that's an NaCl. It's all one huge NaCl. In our example, what we see this in is like diamonds. So in a diamond, you have carbon, 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 right? A diamond is not an accumulation or a collection of lots of little tiny diamonds. It's one big giant diamond. So it's going to share some properties of both covalent and ionic. So it's going to have the high melting points that we would see in ionic bonds, right? Because in order to actually melt this thing, I'm going to have to break a covalent bond, not a hydrogen bond. And I'm going to see the crystalline structures as well. But what I'm not going to see is conductivity. Because even if I try and dissolve this in water, even if I melt this, even if I eventually do break these covalent bonds, there are no charges for me to work with, and so it could never conduct electricity. Now, the next one and the last one that we have here are metallic bonds. Metallic bonds are quite a bit different. Now, in metallic bonds, we don't have two different elements that are present. We have the same element usually repeating over and over and over again, although we can mix metals. We can have a mixture of metals, and we'll talk about that in a second. But in this situation, these electrons are not localized. They are delocalized. Now, what does that mean? If we look back at a covalent bond, the electrons are locked in place. They are never going to move out of this bond. In an ionic bond, the electron has been moved over to here. It is now stuck in this position, and it is never going to move. That is not the case with metallic bonds. Metallic bonds are happy to let their electrons flow and share. They are not possessive. This electron looks like it belongs to this metal, and this one looks like it belongs to this metal, but that's not the case. You might see this electron hanging out next to this guy, and in 5 minutes, this electron might be down here, and this one might be over here. They're constantly flowing and moving, and so it changes our characteristics quite a bit. We say that it's like a sea of electrons. And so because of this, it's not going to be hard and brittle. If I smash this atom over next to this one, they want to repel, but what's going to happen? Electrons are just going to flow right in between them. And so they're malleable. It means that we could bend them. They're ductile. We can stretch them into wires. And because the electrons are constantly flowing, our charge is constantly moving, and so they conduct electricity all the time. And it looks like I forgot to put that in. So they conduct all the time. They're also normally going to have high melting points, although there are some metals with fairly low melting points. The majority of them are high. Now, the last thing is we can mix our metals together. This does happen, and we call that an alloy. So why would we want to mix two metals together? Well, the reason is because we often get superior characteristics. So iron, for example, is extremely hard. It's very strong. We use it in most of our products, but it's very, very prone to rust. If you built an iron out of a building out of pure iron, it would rust away in a few years. So what we do is we add a little bit of chromium to our iron, and what that does is it provides corrosion resistance, and we no longer get this rusting. We get stainless steel. So we can mix a lot of different things, and this gives us things like brass and bronze, all the stainless steels. You could do it for jewelry as well. You can have like rose gold instead of regular gold. So when we do this, there are two ways that the metals can mix. They can be either interstitial or they can be substitutional. So in a substitutional, what we have are two atoms that are roughly the same size. So if we look, a copper atom and a zinc atom are roughly the same size. So if this was all copper, you can simply pluck one of them out and place the zinc in its original location. And this works nicely because, like I said, metals are crystals. They don't appear to be crystals to our naked eye, but they are. And so there's a very ordered pattern in how these atoms are going into the metals. And so plucking one out and replacing the other is a pretty easy thing. But because they are these crystals, you'll notice that there's these big open empty areas in there. And so you also have the option of, if you have a really small atom, you could stick it into the gaps. And so we call this an interstitial alloy. And so when we wedge things into the gaps like this, it usually stiffens up our crystal, and it makes it a lot harder and a lot stronger. So this is where a lot of our steels are going to come from. Like iron is interstitial with carbon. So it doesn't always have to be a metal. Carbon is sort of one of the few situations where we use a non-metal in there. Most of the time it should always be metals though. So at this point, my voice is given out. I hope you guys got all the information that you needed. Let me know if you have any questions.